Exercise 9. Develop a math model for the problem. Describe the type of math problem that has resulted. Using assistance from the TI Nspire CAS, solve the math problem and interpret the solution. An industrial welder manufacturer in the U.S. wants to participate in an industrial products expo held in Rio de Janeiro. The manufacturer is confident it can ship a standard 20-foot container packed with welders and sell all of them. The plan is to offer two models, the 3pH model, which requires three-phase electricity, and the ENG model, which is engine-driven and thus portable. The 3pH model has a production cost of $2,700 and will retail at the show for $6,000. It weighs 800 pounds and occupies a packaged volume of 18 cubic feet. The ENG model has a production cost of $2,400 and will retail at the show for $5,000. It weighs 350 pounds and has a packaged volume of 12 cubic feet. A 20-foot shipping container has a volume of approximately 1,200 cubic feet and a maximum cargo weight of 48,000 pounds. The manufacturer wants to avoid a large tariff imposed if the production cost of the shipment exceeds $216,000. How many of each welder model should be shipped in order to achieve the maximum profit? Okay, let's see. A couple of variables that are surely needed here, and we might start off by let x equal the number of 3pH model welders to ship, and similarly we let y equal the number of ENG model welders to ship. Most important quantity, I suppose, would have to be that profit. That's what we're trying to maximize here. So we furthermore can let P equal the profit. And let's see, what about that? Well, we have the production cost and the retail price for the 3pH model. One 3pH model costs $2,700 to manufacture, retails at $6,000. Okay, so that difference there will be our profit on one of them. Alright, so that would be, let's see, 6,000 minus 2,700. That's for one welder. It would be multiplied by the number of 3pH models to get the total profits from the 3pH sales. And then there's profit derived from selling the ENG models. It says those cost $2,400 to produce. They're retailing for $5,000. So we'd have here a 5,000 minus production cost, $2,400. That's for one of them, times y to get the total profit from all the ENG type welders. And then I suppose we could just do a little arithmetic to simplify this. 3,300x plus 2,600y. Okay, and again we seek to maximize this. Okay, what's the domain of this function? Subject to. Well, one concern, certainly a physical sense. Okay, we're talking about a number of welding machines to be shipping, so you can't have negative numbers to ship, so we certainly require x to be greater than or equal to 0 and y greater than or equal to 0. So there's one type of pair of inequalities. Okay, something else. You can't very well ship 2/3 of a welder. You either ship a welder or you don't. So we also then have the idea that x and y must be non-negative integers. Okay, pair of statements 2 there. Let's see, what else is going on here? Besides just physical sense, we have this shipping container. It's got a volume, maximum volume, so there's a limitation to the amount of volume we can ship here. Alright, so we have here limitation of container volume. Okay, let's see. If we look over the specs for the 3 pH welder, it says it occupies a packaged volume of 18 cubic feet. Alright, that's for one of them. So if we had X of them, we got 18X amount of volume consumed by 3 pH welders. Similarly, the E&G model says it has a packaged volume of 12 cubic feet for one. So we're looking at plus 12Y for the E&G model volume overall, and the container has only got 1200 cubic feet available, so this has to be less than or equal to 1200. We could consider that inequality 3. Sometimes you get tempted to do some simplification, algebraic simplification, which may or may not be helpful. It looks like here both sides divide by 6 rather easily, so okay, let's try that. And then we could have 3x plus 2y less than or equal to 200. We call that 3a. Alright, let's see, what else have we got? Okay, this container, besides having a limited volume, it also has a limited cargo weight here. It says that the container has a maximum cargo weight of 48,000 pounds. Okay, so we've got here limitation of cargo weight. Let's look at that model 3 pH. The specs there say it weighs 800 pounds for one, so 800X for all of them. And then there are the E&G models being shipped. The specs point out one of them weighs 350 pounds, so 350Y for all of them. And now this has got to be less than or equal to that 48,000 pounds. Okay, we could call this 4. Suppose you could divide both sides by 10 immediately, and then you could even, if you wanted, divide both sides by 5, I suppose. A. Okay, let's see, what else is to concern us? The manufacturer wants to avoid the large tariff, and this occurs if the production cost exceeds $216,000. Okay, there's another concern. So basically we're going to require production cost less than or equal to $216,000. And that translates into a math statement of, well, the model has a production cost of 2,700 X for the total there. And then looking on to the specs for the E&G, it has a production cost of 2,400 and times Y for all of them. Got to have that less than or equal to 216,000. Okay, there could be number 5. Perhaps you decide to divide both sides by 100 very conveniently, and I suppose you even, let's see, 2 and 1 is 3 and 6 is 9, divisible by 3. Okay, both sides divide by 3 if you want to persist on this, and then that would leave us with 3 goes into the 21 7 times, and then into 6 2 times 0. Okay. Alright, anything else? That seems to exhaust all of the restrictions and limitations. I suppose it's time to take a look at our math model here. Okay, so what about this math model? We are to maximize this profit P here. The function formulation is a linear function. Okay. Now what about the domain? What's it determined by? A lot of inequalities, and all of them almost, in fact, all these inequalities are linear inequalities. This puts this problem into the realm of linear programming, but wait, X and Y must be non-negative integers. Okay. Alright. With this restriction, this actually puts it into the world of integer programming. Okay, so let's identify this math model. This math model is an integer programming problem. Okay. However, we did notice, except for this restriction number 2, the integer requirement, it is otherwise a linear programming problem. So we might notice that. However, except for 2 there, it is a linear programming problem. Okay, well, that being the case, what we might be able to succeed with is to actually solve this as a linear programming problem if all the coordinates of the vertices turn out to have integers, turn out to be integers rather, we can succeed. Okay, so here can be our strategy, and we'll call it initial strategy. Solve as a linear programming problem if all coordinates of the vertices are integers. This strategy succeeds. If you've done the other exercises on this exercise set, you've already encountered just such a situation and in fact succeeded just by using this strategy. So we'll try it again here. Now we're getting ready to head over to the Nspire to work further. Well, anticipating graphing the domain on the Nspire, we will probably like to have these inequalities with y solved for. Okay, so let's take care of that right now. Now we can keep track mentally of x greater than 0, y greater than 0. This puts us in the first quadrant or on the axes. We're ignoring the integer part for now. Here, okay, let's put this in red. We'll need to solving for y, we subtract 3x, divide both sides by 2. We've got this also expressible as y less than or equal to 200 minus 3x divide by 2. Okay. For the number 4 restriction, here we could take this, come over here, solve for y. We'd have y less than or equal to, in parentheses, 960 minus saying 16x, and then that is divided by 7. Okay, and number 5 here. Alright, solving for y. Subtract 9x from both sides, divide both sides by 8. We have a y less than or equal to, in parentheses, 720 minus 9x divided by 8. Okay, well, let's go to the Nspire. Okay, at the Nspire, let's open up a new document and let's add a graph. Okay, I suppose we could just jump into the entry line here and start putting in the inequalities that we need. We plan to mentally keep track of the first quadrant or axis idea, and this then moves our attention to number 3, where we have a backspace here, and it's a less than or equal to, parentheses, we got the 200 minus 3x parenthesis divided by 2, and enter. Okay, let's see here. Maybe we would like to have see a little bit of what's going on here before we proceed even further. Let's see, we could, maybe we try zooming out. Maybe that might be a way to get things started here. So let's zoom out a little bit. Okay, now we start to see some activity here. Alright, I'll put away the zoom out tool. Maybe I will pull this in the direction of having the first quadrant be prominent. And now let's go ahead and continue on. Okay, second one, which would be number 4 in our case. We've got a y less than or equal to, and in parentheses we're looking at 960 minus 16x and that's all divided by 7. Okay. Let's see. So, and we're keeping track mentally of the overall intersection, right? So right now it's it's in quadrant 1 or axes and the olive green here so far. If this got to be like a 4 inequalities, I would probably use that method of graphing the complement and looking for the unshaded white region. But here, at 3 is sort of, at least for me, the maximum where I think I can clearly see the overall intersection of 3 inequalities and not lose control of the question. Okay, time to go to inequality number 5. Okay, it's also a less than or equal to type. And in this case here, we've got the parenthesis 720 subtraction a 9x parenthesis, and that's divided by 8. Okay, here. Let's see, something else I might do. This is going to get a little crowded if I start having all the labels of the inequalities appear at first, because I'm after a vertex search here, which looks to be a little bit involved. So I think I'll return to the home screen, and for the settings I'll go to the graphs menu. I want it right now to automatically hide plot labels, because otherwise I'm afraid there's going to be too much going on in this graph. It's going to get too congested. So okay, there. Okay, let's go ahead and return back here. And now let's see. We might improve the prominence of the domain here a little bit. So I think I'm going to do one more zooming in. This time, maybe a zoom box. Alright, I want to get a little out in here to ensure getting the X and Y axes, and then I want the box to contain the very dark blue region and not too much more than that. Okay, about there. Alright, there we go. I'll put away that tool, escape. Now, on to the work at hand. Alright, for our vertices, of course we see 0, 0 as a vertex. We're keeping track mentally of the first quadrant. Alright, up here, the y-intercept of this blue line, we can get that pretty easily by doing a trace, and then immediately typing in a 0 for the x and hitting enter. Okay, and then enter again to get that to appear on the graph. And then I think I'll put that escape from that for a minute. Alright, so we got 0, 9 to here. Good. Integer coordinates. Maybe I'll put that just over here. Now there's this point of intersection of the red boundary line and the blue boundary line. Let's go ahead and get that. We can do that by analyze graph intersection of this blue line. Alright, let's just identify the second graph. Well, that's the red line. Now for a lower bound, about there, click, and then we glide over and watch for the intersection to appear. It does. Hit enter, and then we can put this to a nice convenient location. But you know what? What's the significance of this result? It's game over, huh? That x coordinate, it's not an integer. Okay, so our linear programming strategy has, at this point, just been defeated. Okay, well, you know, we can still get some information out of this. While we're here, we might as well go ahead and get the domain clearly identified. It just takes too much more effort. It makes our solution look more clear as well. So let's go ahead and let's get another intersection here. Now that was the red line I chose to analyze the graph on. The second graph is then this green line for a lower bound about there. Gliding over. There's another intersection. Enter to get it to be pasted onto the graph. Let's move it to a nice location. And also notice both coordinates here are not integers. Okay, and the last vertex here, to complete our domain description, would be where this green line hits the x-axis, we can do that by tracing this and then bring the tracer line down, because the zero will automatically appear. Okay, it does, and enter to get it on here. And let's put away this tracing tool. Let me take this and move this a little more in sight. Okay, so 60 does have integer coordinates. Alright, so here we are. Can't use our linear programming anymore, but we do have our domain picture here. What shall we do? Okay, now it's a true integer programming problem. We basically, or at least one primitive strategy, but effective here, and that is we could simply evaluate this profit function at each point in the domain and choose the highest profit. It's a lot of points done manually, so this really calls for a computer program. While this is here, I suppose it's a good time to make note of the idea that the x's range from 0 out to 60, and the y's range from 0 out to 90. But then they're of course restricted by all of these assorted boundary lines as we look in the domain graph here. Okay, but this actually does give us a little bit of a starting idea for our program that we want to write that will evaluate the profit function at each xy, which has integer coordinates. Okay, let's go to that next. Okay, so designing a program. On the left-hand column, we'll describe in words what we plan to do, and on the right, we can put in the Nspire source code. Okay, for starters, to keep our program organized, it might be nice to actually verbally or in a worded description explain what we're planning to do here at first. And so here we're thinking about the this first module will seek the maximum profit and a point at which it occurs. Okay, now as far as the computer code goes, what do we have in mind here? Alright, in helping to communicate our program to someone reading it, this is a good opportunity to put a comment that says just what we've written here. Alright, on the Nspire, to insert a comment into a program, you use this kind of copyright symbol, and then you write here. It's just a matter of really rewriting what we have expressed here. So I think as a shorthand I'll take an arrow and point that we intend to rewrite this text right here following the comment command on the Nspire. Alright, having explained what we have in mind here, how are we going to start to do this? Okay, what we might do is first generate an array of points which have all integer coordinates and keep them where x is between 0 and 60 and y is between 0 and 90, which is what we saw in our graph of the domain, that the x's and y's are so constrained. So that could be a starting point. Let's write that down. Okay, so generate a rectangular array of integer coordinate points, x going from 0 to 60, y 0 to 90. What kind of source code will do this? Okay, we can use counter loops to do this, and the coding for that is, first of all, we have a for, and now making x go from 0 to 60 in integer increments, we would first identify the variable, the starting number, 0 in this case, the end number, 60 in this case, and the default increment is 1. If you're ever using a counter loop and you want to increment by 2, 3, or 4 or whatever, you would put a fourth argument in this sequence and designate it here. But the default is 1 unit, so we can do nothing else and have this. Okay, this needs to have an end statement that goes with it. We could put that down about here. Now, we also want to generate y's going from 0 to 90. So, interior to this counter loop, another counter loop for the y's. And its N4 statement inside here. Okay, so this generates xy's as we need to get started. One item does appear here, a slight little problem, and that's that if you use a counter loop, and we've chosen this variable x and the variable y here, which is a good choice for the counter variables because it also reflects our definition of x and y in the initial formulation of this question. Trouble is, for the Nspire, we try not to create variables out of simply x and y because it can cause troubles in other applications where the Nspire needs to use x and y itself. So what we can do to avoid problems here is we can define x and y to be local variables just for this program. So up here we could have a local definition, and then we put in the variables x and y defined to be local. Okay, what's next to do? Okay, now we have this rectangular array of these integer coordinate points. We know we need to basically create a filter which passes on only those points which are in the domain. Okay, so our next item, we're going to create a filter which passes on only those points which are in the domain. Okay, how can we create a filter which just passes through the points that are in the domain? Alright, we can use a conditional statement. An if-then statement would work well here. So how would this work? We could say if, now we need our x and y's to meet those inequalities that were specified in our formulation of this question. Rather than rewrite them here explicitly, let me use the numbers that we have designated in our formulation. So we had inequality 3. So right now I'll just put its reference here. Then we want an and, a logical operator here. So if you write and in the Nspire, that's what that becomes, a logical operator here. And 4 and 5. Okay, now this would give us all the restrictions of the domain, and then we could have our then, and now we can proceed in here. We need to put the corresponding end of the statement down here, like so. Okay, now that we've passed forward into here, only the points that are really in the domain, what shall we do next? Okay, now we need to be determining which ones have the maximum value, and we basically need to evaluate the profit function and then keep updating the maximum value as we encounter higher and higher values of profit, as we keep on substituting the various xy's into the profit function. Okay, so let's write that down in description. Okay, so we want to evaluate the profit function of at xy and continuously store the highest encountered value as we go along here. Alright, so how would that look in code? Alright, let's see. We could come in here and say if P of xy is greater than, we'll call the maximum storage location Pmax, then, alright, and so in other words, if we actually encounter something which has a new highest value, we should store it into the highest value location. So in other words, we will then say that Pmax will be assigned to P of xy. Also, while we've got this P max stored away, may as well keep its x and y coordinates as well. That way at least we have one point at which the maximum occurs, and so then we could furthermore say x max assigned to be x and y max assigned to be y. A little trouble here, and that's that right now this program does not have a p of xy function, and we have not put it in the problem in any other page yet, so this will need to have a definition. Okay, let's go back up in here, and right after our local statement, it's probably a good time to go ahead and say define p of x, y equal to, and for this we just refer back to our original problem formulation. We said that the profit function value at x, y is equal to 3300x plus 2600y. Okay, now that's good. This now has some meaning for the p of x, y. Another little item though is this. We are comparing the p of x, y to the p max, and then updating it to be p max if it is actually greater than it. However, upon the first time this comparison is made, there's nothing in p max, so this will cause troubles. This means we need to also provide an initial value for p max. So again, something that needs to go on prior to even getting into the counter loops here would then be to also define an initial p max value, and I like to do something that's sort of nonsensible, so that in case it doesn't get updated, I will know it. So perhaps a p max equal to, say, -1, something like that. This way, in case I run this program and I find out that p max is equal to -1, even out here, I'll know that something is wrong and it's not getting updated within this conditional statement. Okay, anything else? Yes, we need the corresponding end for this if-then construct. So right here, that code there. Now, once we have all this, what else would we like to do? Well, looks like we'd like to state the results of this module. Okay, and for that, we could use a display statement, display command, and for that here, we could say something like the maximum profit is p max, and then another couple sentences might be to say that this is achieved when by shipping x max of model 3ph and y max of model ENG. In code, we have to put any kind of text in quotations. Okay, here's how it would look. Okay, so our first sentence, the maximum profit is, that's all in quotations, comma. Record the p max, and since it was to be a sentence, I actually need a period to end the sentence, so I then have a quotations, just a period there. Then another display command, text. This is achieved by shipping the x max variable, records there, another comma, more text, quotations, model 3ph and quotations, and another variable, the y max appears there, and then model ENG. Okay, so we seem to have things designed on paper. Let's put this into the Nspire and see if we can at least get this first module running successfully. Alright, back at the Nspire. It's time to open up another page. Control, Add Page. To access the program editor, which is what we want to do now, there's two ways to do this. One is to open up a calculator application and open up the program editor from there. I do not choose to do it that way because then you have a split page with calculator half the page and program editor on the other half, whereas I like a lot of room to write programs. So another method is to come here and click directly on the Documents tab again, and this time go to Insert, and then go to Program Editor and add a new program. Okay, let's input its name here. We can call this Exercise 9. And the rest I just leave the program and library access to the defaults. Click on OK. Alright, as you see, a couple things. First, the Exercise 9 has been defined as a program, and you see that fact also up here in the status bar. Exercise 9 is the name of the program. That's in the left. Over here on the right, this is telling us that right now we're on line 0 of a one-line program. Here's our one line. It's actually right here waiting for us to do something. It doesn't actually count the definition of the Exercise 9 as a program, nor the end of program statement as part of the program, really. Okay, so here we are, line 1. What to do? Well, we want to put our comment first to describe just what we have in mind for this first module. To do that, go to Menu, Actions. Notice number 8 here is Insert Comment. Okay, we get that little copyright symbol, and it's time to kind of keyboard in just what we wrote here on our worded description. Alright, after you finish the keyboarding, look it over because there's no spell check, and hit enter. And now we can go to our next line, which is where we defined x and y to be local variables. Alright, to do that, we'll need to go to the menu. We're going to go to the Define Variables and Local. Okay, here we put in our x, comma, y, and enter to get ready for another new line. Here's where we could define our profit function, p of xy. Okay, so time to go to the menu, Define Variables. Number 2 is Define. Okay, here's what we'll do, just as we've written. P of xy equal to 3300x plus 2600y. And enter. Okay, we're on line number 4, as you see in the upper right hand corner there. And for us, it's time to initialize the value of the Pmax. Pmax assigned to B. Okay, Control assigned to B, -1, and enter. Okay, it's time to get our counter loops going here. So let's go to the... Actually, I would like to leave one more space, since this first part of the program is kind of just all definitions and comment. One line to kind of start a really core statement here, and off to the menu. These counter loops are tied up in the Control menu. You notice here we are, the 4 and 4. This is what we want. Okay, and it's already got some commas there waiting for us. And so we first put in our, as we've written down, our variable x. I'm going to forward arrow to get past that first comma, and then our 0 for the initial value of x. I'm going to forward arrow to get past that other comma, and 60, and enter. Now, by the way, we're on the next line of program, but you notice when this Nspire puts in the for command, it puts in its terminal command as well that always goes with it. See, the N4 is already there. Alright, now we are interior to this loop. Time to put in another counter loop. As before, menu, controls, number 5, 4, and 4. And this time it's Y. Forward arrow, get past that comma. Initial value is 0. forward arrow, get past the comma, 90, and enter. If you look down, you see we have indeed got the second and 4 there. I think I'm going to backspace to clear the space between these two, since I know I don't want to put anything between them. And now come back here to line number 8 here. Following our plan, it's time to put a conditional if-then statement. I want to kind of indent this so that it shows I am interior to my loops here a little more dramatically. So I take about 4 spaces indentation, and now let's go to the menu, find the conditional if-then. It's also part of the control commands, and it is right here, if then Endif. Okay, now as far as this if goes, here's where we need to look back at our original problem formulation to find the inequality number 3 in its primitive format. It says 18x plus 12y need this to be less than or equal to 1200. And watch how the font changes with respect to what letters you put in for and. In other words, you start with A, N, C, all italics, right? But once I put the D, boom, changes to regular font because and is recognized as being a logical operator by the Nspire. Okay, and it's time for inequality number 4. In its primitive format, that looked like 800x plus 350y less than or equal to 48,000. Control inequalities palette, 48,000. Okay. Another and, A-N-D. And inequality number 5 in its primitive format looked like 2,700x plus 2,400y less than or equal to 216,000. Okay, I will forward arrow to confirm that the then statement is in sight. Alright, now I can push enter to get to the next part of this. Alright, once inside this conditional if, we are planning to put in another conditional if statement to help keep my program organized. I will put a few indentations here to go to this level of conditional statement. And now to the menu, control, if then, Endif structure. Alright, in this case we want to have the determination whether or not p of xy is greater than p max. So like so, and then next line. Alright, if the profit function is greater than the present p max, here come all the reassignments. It's time for p max assigned to be p of xy we have our x max assigned to be x. We have our y max assigned to be y. Alright, now we should have the corresponding Endif statement down below this somewhere. Alright, let's delete this line. Oops, bring back the y. Okay, Endif there. We don't need this line in the program. Suppose we could delete that. Now it's time to exit these counter loops, and here's where we were going to enter some display instructions. So maybe one more line, and for display that's going to the menu, input output, display, put in a quotation mark. You notice the Nspire puts in the second quotation mark for you. It leaves you with just a text box for you to concern yourself with, so resist putting in second quotation marks by mistake. It's kind of a common error, at least for me. Otherwise, let's keyboard in what we have written here. Alright, so we have the maximum profit is Pmax variable, and then a period to end our sentence. Let's enter for a second sentence here. We have another display command, so back to the menu, input output, display, and here's where we're going to say this is achieved by shipping Xmax model 3PH and Ymax model ENG, just as we've written there in our handwritten version. Okay, so there's the keyboarding here. So it says this is achieved by shipping Xmax variable model 3PH and the Ymax model ENG. Okay, and now this brings us really to the end of this first module. We do have another concern with our program, but right now let's get this much checked out and running. Let's make sure this program can at least pick off the maximum profit and one point at which it occurs. Okay, so let me go ahead and have this much program checked over and stored. How is that done? Control B. Control B. See there in the status bar? It says exercise 9 stored successfully. Okay, great. Since it's done that, let's then see if this much of the program runs as we're hoping, which means let's open up another page. Let's add a calculator. And if we now go to the variables menu, there we see our exercise 9 is a variable, and that icon you see there designated as being a program variable. Okay, I'm going to push enter to paste it on the page here, and then I'll push enter again to execute the program. Cross your fingers. Oh, okay, very nice. Came up with a conclusion. Maximum profit is 243,200. Oh, you know what's missing there? Units of measure. You need the dollars symbol. Okay, we can go back and correct that really easily. And this is achieved by shipping 28 model 3PH and 58 model ENG. Ah, okay, that's kind of interesting. We will check that, but let's go back and change that program a little bit to get the dollar symbol. So I'm going to go back to page 2, and right in here I want to put the dollar symbol. Okay, once again Control B. It's stored successfully. Back to page 3, back to the variables menu to get, and by the way, you notice all of a sudden new variables have just all of a sudden added to our collection of variables. That's because once the program runs, it has defined P, the P function we put in there. It says defined Pmax and Xmax and Ymax. You notice X and Y are not in this list. Why is that? Because remember, we carefully define them to be local variables, so they're variables only within the program, not throughout the problem like the other variables become. Okay, anyway, we want to take one more try at exercise 9 just to fine-tune how it comes out. There, okay, now it has the units of measure for that number of that profit there, the dollar sign. Okay, and now this much is in order. Okay, let's begin to check over this conclusion here. 28 model 3PHs and 58 model ENGs. One thing we might first do and see if that even looks to be a point in the domain of the profit function. So let's return to the first page of this, where we had sketched the, we had started to sketch the domain. Here we were initially thinking maybe a linear programming problem approach would work here. Maybe since we have this graph here, let's go ahead and finish it up and clearly mark off the domain, or label the domain of this function. And to do that, we could go here to the menu and go to the shapes and go to the polygon drawing tool perhaps. And let's remember we're supposed to be in the first quadrant or on the axis, so there's a vertex. There's one. There's one. There's one. There's one. And back to here. Okay, let's escape from the polygon tool, and now let's go ahead and shade the starting domain region. Okay, have the polygon. Let's go to coloring, fill color. Let's pick something, dark blue, navy. Alright, also let's, while we're at it, get the boundary line, the same dark blue color. Okay, there. And perhaps a little bit of labeling here. We don't have this labeled as our domain, and we actually don't want to label this as the domain because, remember, x and y need to be integers. So let's put some text in. We'll say that the domain are the integer coordinate points lying on the dark blue polygonal region. And for that, you just have to go to text and begin writing. Okay, so here we have the domain labeled. Now, what about this claimed optimal solution situation, which occurs supposedly at the point 2858? Let's see if that looks to lie on the domain here. And for that, we could go and pick out a points and lines, do a point, and start putting in some coordinates. So put in the parenthesis, and it's waiting for an x coordinate where you want 28, then hit enter. Now waiting for a y coordinate 58, and then hit enter. And now that point is on here. I'll push escape to exit the point tool. Now it's hard to see because it's apparently very close to this other point here. Okay, so maybe it's time to do a little bit of zooming in, and since this is a kind of a nice graph of the domain, I want to leave this as part of our solution. So what we can do is we can do this. Let's go with control, look at all the pages. Let's take this graph, copy it, and then paste up a second version of it, and now we will still have the domain graph available to us as we can work on this graph as far as zooming in goes. Alright, now we're interested in getting very close to that optimal point, 2858. So let's go ahead and do some zooming. Perhaps a zoom box might be an idea. Alright, so there's a corner, and maybe here's another corner. Okay, another zoom box. Perhaps a corner there. Corner there. Okay, put the tool away by hitting escape, and maybe I'll kind of slide this graph about here. Okay, this here, 090, doesn't really belong on this zoomed in graph anymore, so let's delete that. This point here, 60, also doesn't belong on this zoomed in graph. Let's delete that as well. Let's take this point and put its coordinates back on there. Alright, that was the vertex from the linear programming idea. Here is the optimal point, so we think. Okay, that goes there. Well, it does look to indeed be in the domain of the function, just barely, right there on the borderline apparently. And what might be also kind of interesting is this. As solved as a linear programming problem, this vertex here probably would turn out to be an optimal point, and what you probably then would be tempted to do would be to then say, well, if this is the if the maximum value occurs here at this vertex, then since we need all integer coordinates, we would just go to the nearest integer coordinate point and assume that is probably the correct answer. Alright, so we can do two things. We can try this, and it will, one, see what could go wrong with a linear programming approximation tactic such as that, and two, give us a check on our current solution. Alright, let's get the actual domain points on this dark blue region here. So how can we do that? We'd like to have all integer coordinate points to appear. We could do that by first going to the window and arranging it so that our scaling on each axis is 1 per unit, because the grid uses the window, the scaling, to decide how it's going to set up the grid points. So let's go here, we'll go to Windows Zoom, let's go to the settings, here in the X scale. Okay, let's go with entering a value, and it's 1. Alright, let's go here to the Y scaling. Let's go with entering a value and make it 1 apiece. Click on OK. Now, let's go back here and second menu. And let's do the hide show the grid. Okay, there we are. See the little white points? Those are the actual domain elements. Now as we see this, let me sort of slide this graph over a little bit. Now, what seems to be the situation? Well, in solving a linear programming problem, this would be a likely point at which you think the maximum would occur. So let's go ahead and let's take the nearest integer coordinates to the vertex and see what becomes of them. It's kind of interesting. And okay, let's first get these nearby candidates labeled. So how can we do that? We could go here and go to the points and lines, point on at first, and there, click once, click twice, we get a point there, and here's another candidate right here. Click once to identify we want to point on there, click again to get the point on. Okay, let's put away the point on tool. Let's put the coordinates on these points here. So we will right click and go with coordinates and equations. Okay, so this is the point 2759 over here. Right clicking, coordinates equations, that's the point 2660. Alright, so now we have this nice looking zoomed in version of the claimed optimal point and the vertex of a linear programming approach and the nearby coordinate points there. Okay, so let's take a look at what goes on to the profit at the point 2660, for instance. This is a good challenge to our optimal solution claim. Alright, so let's go back. And at this point we would probably do well to have a page for some text writing. So let's get a notes page going. For that, let's first take this, copy and paste it onto notes. And here we will open up another page, add a notes application, paste this conclusion here. As for checking, let's challenge this claimed optimal solution with the point 2660. Alright, so we've keyboarded in some text here. As for a check, we can challenge this claimed optimal XY by considering the near to vertex, point 2660. The profit function value at this point is, and now I am not going to use the profit function I formulated in the program. In fact, that's part of something I check. I am actually going back to the original formulation of this question and noticing that we said the profit there was going to be 3,300 times x. So that would be, in this case, times 26 plus, and we have the 2,600 times y, In this case, that would say 60. Alright, to compute this in a notes page, I need this to be a math box. So let me just go here and convert this to a math box. Now we can enter it. Okay. And let's make this so that there's an equal sign there. So for the attributes, the symbol, the equal sign. Okay, there. And to make this a complete sentence, with the units of measure on this last number are dollars. Okay, and what do we think there? That generated $241,800. Well, the claimed maximum profit is up at $243,200. Okay, that's nice to see for two reasons. One, that the claimed optimal has a larger profit than this challenger. Secondly, since this point was actually rather near to the optimal domain point, we would like to at least see the types of money involved in the profit as having the same order of magnitude, certainly. Otherwise, we would think something is wrong in the calculation as well. Since both of them are in the $240,000 vicinity, this is looking good all the way around. Okay, so we make a little statement about that. Okay, so since the claimed optimal profit is larger than this challenger profit and of the same order of magnitude, it appears the conclusion is correct. Okay, now there's another issue though that has not been addressed yet. We do seem to have a grip on what the maximum profit is, and we have a point at which it occurs, which means we know we're able to claim how many of the model 3pH welders and how many of the model E&G welders to ship. But what we haven't actually looked at yet is, are there other shipments that would also yield this same profit? In our program, we simply really determined what was the maximum profit available, and we pretty much stored whatever point gave that to us. But what could be overlooked is maybe there is another or even several other ways to achieve this same profit, and as a part of our solution process, we're responsible for that also. So let's make a note of that, and then we will work on that problem next. Okay, so a second consideration is to determine if there are other shipments which would also yield this same maximum profit. A second module of our computer program is needed here, and that's where we will go to work next. Okay, we have returned to the program design to come up with a second module, and we're going to have a description here that this second module seeks additional points x, y, which also yield the maximum profit Pmax. Okay, written about like so, and this would be nice to help describe our program. So what we can do is we can use the comment command here and simply just rewrite what we have here in the comment section. Okay, ready to begin the core of the program now. Okay, so the basic strategy is to simply process all the points through and find out which ones actually are yielding Pmax as their value, and record them if we find such. Okay, so getting started, we would probably first regenerate that rectangular array of points where x goes from 0 to 60 and y goes 0 to 90. Okay, and the code for accomplishing this is, as before, to use a couple of counter loops. So we could say here for x lower number, final number, and then that gets completed with an N4 statement. Inside this, another counter loop for y variable, lower number, largest number, and cap it off with an N4 statement. And we already have set up from the first module x and y as local variables, so there's no problems with that. Alright, the next step might be to now create a filter that passes on the xy's that are in the domain and satisfy their value of profit function as being the maximum value. So here we could write, okay, so create a filter that passes on points xy which are in the domain and satisfy p of xy equal to p max. Okay, filter best treated with a conditional statement similar to what we have done earlier. So let's go with the if then Endif structure. So here we could have if. Now what are those conditions? We want to put on the remaining demands of the domain, and as before we could just for now refer to those as the inequalities 3 and 4 and 5 and, okay, now there's more in this case. We want to have and p of x y equal to p max. Now if we just have this for the conditions, we'll actually end up relocating the very same original point that we already have. So let's also exclude that, and we can do that by saying and x. Okay, to make sure it's not the same point, we need two things. The x-coordinate cannot equal the x max, or the y cannot equal the y max. So I now actually need a parenthesis to say x not equal to x max, or y not equal to y max. Okay, so it's got to satisfy one of these two conditions, otherwise it's not a unique point here. So we might even change our description a little bit. We are creating a filter that passes on unique. Maybe squeeze that in. Okay, so we have that. Now this has to be paired with its end statement, and also we have our then, and then down here and if. Okay, now what else do we want to do? Now that we have passed on all these points that are in the domain and they satisfy the profit function value being p max, okay, we want to know about those. In fact, we may as well simply display the result if we find such a thing. That would be the next thing. No point in storing it somewhere. It's time to really go ahead and display. So we could here have display any such points. And so here in the then, after the then, we could have here a display command, and we could have a sentence such as the maximum profit can also be achieved by shipping X model 3PH and Y model ENG. Okay, so display something like that, this sentence here, with the report out of the discovery of X and Y. And this will just keep on making this sentence recur with any such X and Y's that get discovered. A final thing that would be kind of nice here would be, what if there are no other XY's that yield the maximum profit? What if we only have the one result there? Okay, well, I guess we could just sort of like leave it and have nothing else said, but it might look nice to show that we've gone to the effort to checking for just that situation and making it abundantly clear that we've done so by having a statement pointing that out if it occurs. Now, what could we say here? Alright, so in other words, we're trying to say if no such points are discovered, we want to effectively state this. Okay, so if no other points yield the maximum profit, state this. Alright, well, we want to have we need some indicator that triggers us to know that no other points were found, and one way to do that would be to create a counter variable. We could call it a alternative count, since it's counting the alternative ways to achieve the maximum. Maybe we'll call it alt count for short, and we could initiate its value. Okay, that needs to be done way up here. So let's say alt count, this new counter here, we'll assign it to equal 0. It starts off, there are no additional points found. If we get into this filter here and get past it and display something, then each time we do this, we could actually make alt count go up one notch. So in other words, right here, we could put in an alt count assigned to be alt count plus 1. Okay, and then after this program goes through all of its counter loops, in the end we could check out for the condition that if the alt count equaled 0, okay, never got changed, this is when we went to state there are no other ways to achieve the maximum profit. Now this is a really simple condition. If the alternate count variable equals 0 and then display, right? For that we could use the simplest conditional of all. It's just a simple if statement. If you have a situation where you have a conditional that has some condition and then you just want the very following step of the program executed, you can use just a simple if, and that is just suited for us here. So we could have if we have our condition alt count equals 0, and you don't have to put then for this statement. It simply automatically decides based on this whether to do this very next step or to go past it. And here, if the alt count equals 0, it's time to say something. We could say a display statement and have it say that there are no other ways to achieve this maximum profit. Okay, so something like this here, display there are no other ways to achieve the maximum profit. And that is truly the end of the program here. So here's where we would encounter our end program statement that's already put in, and then we'd be all set. So now it's time to keyboard this all into the Nspire and see what happens. Alright, so let's see. Let's go back to the programming page. Here it is. And let's go down to the end of our first module. Right in here. And perhaps a couple lines here because we're starting a whole second module. Help separate this. And the first item would be to put in our comment about just what this is here. And so we'll need a comment command. That is a matter of going to the menu, Actions, and Insert Comment. Okay. Now we can input there what we have written down already on paper. Okay, so this second module seeks additional points XY, which also yield the maximum profit. Okay, next line, we can go ahead and maybe skip a space from the description and now start the initialization of the alternative counter. So that's a matter of assigned to be 0. Now here come the counter loops and the conditional statement, and since this part has quite a bit of resemblance to what happened in the first module, we might do a copy and paste thing here, because remember, rewriting all of those inequalities is a little bit time consuming and error prone. So maybe we could go ahead and try that. So back up here to our first module. Let's try to start with the first counter loop. Okay, that captures the counter loops and everything interior to them. So here's a chance to do a copy. Go back down to where we were, right here, and we can paste that in there. Okay, now let's go back up. The counter loops are exactly the same, nothing to change there. While we're staring at this entire conditional here is not part of the second module, so we can come in here while we're looking at it and sort of just take out, delete all of that, and the end statement of that conditional can also go. Okay, what we can do is we can come back up here to this conditional, which our module 2 has all three those inequalities. And there's more. We also want to now require that the p of xy equal to p max. So here we got the and p of x y equals to p max, and alright, now we have the idea where we're making sure this point is different from the x min x max that's already been discovered. So here we ensure that by having x not equal to, okay, control relation palette, and over here is the not equal to x max, or logical or y, back to the relations palette to grab the not equal to y max, parenthesis. Okay, let's make sure that then follows. Alright, and the next line we have here a display command, so we can simply keyboard all this in at this point. Okay, so done here. We have the display. The maximum profit can also be achieved by shipping, the end of the quotes, need variable x there. Following that second comma, more quotation to have more text. Model 3ph and then the y, model eng. Okay, next thing would be to uptick the alternative counter by 1 notch, so that's an assigned to be alt count plus 1. Okay, now we go down here. We don't really need this line here, and we don't really need this empty space here. Okay, this looks pretty good here. We now need to come here, and after the counter loops have been completed, we have this last portion of the program that gives us a statement in the event that we do not find any other points that yield the maximum profit. So we were going to use the simple if here. You can go to the menu and you can go to control, and the simple if is number 1 there. Now you can actually type that in with regular keyboarding as well, but there it is on the menu. And now we have alternative count equal to 0. Then we would display. Okay, there are no other ways to achieve the maximum profit. At that point, this should bring us to the end of our program. Alright, let's try Control B, see how this succeeds as far as the Nspire is concerned. Okay, exercise 9 stored successfully. Alright, let's go back to our page that had the calculator. I like to run the program here so that I get all of the text output. If I run it directly on notes, I simply get a done message, so that's why I do it here. We could go ahead to the variables here and grab exercise 9 and enter. Okay, there we are. Looks like there are no other ways to achieve the maximum profit. So what we discovered in module 1 is it. Now let's take this to our notes page. So to do that, let's do a copy and paste. Alright, so when we last left off, we had here a second module of our computer program is needed here. The results, and now we could paste. Okay, now the maximum profit is $243,200. This is achieved by shipping 28 model 3ph and 58 model ENG. There are no other ways to achieve the maximum profit. We've already checked this out earlier in this paragraph, so the last thing I would like to do, I suppose, is to make this bold font, since it is the ultimate conclusion to this problem. And for that, we just go here to formatting, select bold. There we are. Now we have a nice looking prominent conclusion. So let's maybe just I'd like to take a look at this in the computer view, where it's a little easier to see the entire page of each of the important pages here. So let's just do that for a moment. Okay, so here it is, the program in all the source code, and here's the beginning of the program and all of the first module, and then it's followed by the second module here right on through to the end of the program, so we can see that in its entirety. Alright, and here's our notes page. At first we ran the program just on the first module, which, by the way, is a good way to approach a computer program, is make sure each module works one at a time. So in that first module, we at least knew what the maximum profit was, and we had located one shipping policy to create that maximum. Also, of course, in the middle there, we had the check of this answer as well, giving us confidence that this was indeed a correct result. And then we went on and did a second module to see if there were any other points, any other shipping methods that would yield the same maximum profit. We found there were no others, and there in the boldface font is our final conclusion to this question to finish out. Okay, very good.